Hello, everyone. Feel free to ask questions while we're waiting for everybody to log in. Like Mr. Younger, how do you get your hair so curly? I did have a rando walk up to me in Walmart parking lot this weekend and say, "How do you get your head so smooth?" That was awesome.
Good morning.
Good morning. Does anyone have any questions before we get cranking up? Oh crap! I forgot to turn on the practice test. I'll turn on the practice test during lab, so it'll be up at lab. I completely forgot about that. Baby Yoda. People miss that. The screen confuses me. Yeah, I love my Baby Yoda. He's cool. This one's actually kind of creepy. They gave him some kind of weird fingernails. Other than that, he's all right. But these fingernails creep me out. So some people, Sophia, who all of a sudden can't use her mic, blah blah blah. I've asked about tests. So the actual test will come up at least by Friday, but maybe by Thursday. And the practice test will be up. Like I said today, I'll put it up while you guys are in lab. Those of you who have me for lab, and we'll definitely have until Sunday night at 11:59 to complete your trials on the test. Everybody go ahead. Looks like most people are doing it already. Everybody go ahead and chat me your first and last name so we can have that on the roll. Does anyone have any other questions? Somebody asked, will post a sample test. The practice test is really a sample test because I literally am using the same bank of questions that I usually use for my actual test. I reserve the right to change about 10% of the points. So like 10% of the points can come from a completely made up set of questions that you haven't seen yet. I always say 10%. I really allow up to 20%, but I've really never done more than 10%. The final, however, I normally do 10% of only 10% of the points on the final exam come from things other than previous tests. So this gives you another chance to try to learn what you learned or what you're supposed to learn by the midterm and all the other tests. And if you have, then you should be able to do really well in the final. All right, so make sure everybody chats me your first and last name, and we'll go ahead and get started. It looks like no one has any other questions. Emma, did you have a question?
Yeah, I actually did have a couple of homework questions, but
Okay, go for it.
okay.
You want to
So,
share the screen?
yeah, I probably will do that. Hold on, let's see.
Okay, you can go whenever.
Could you make it so that I could share the screen? I think it said that it's
Try it again now. I was doing it just a second ago, so it might have happened while you were trying. Still no go?
hold on. Yeah, okay.
I tried a new setting, so I wasn't sure if I'd done it okay. I have not forgotten the question I got last time, so I'll definitely address that one too. I just haven't done it yet. $321. Okay. T equals 0, particle starts from rest at x equals 0, y equals 0, moves in the xy plane with the acceleration 4I plus 3j meters per second. Assume t is in seconds. Okay, so this is exactly the derivation that I did for you guys to come up with the x equals 1/2 at squared equation. So what you're going to do with this one is you realize that a is actually dv dt. So you'd set that dv sub x over dt equal to 4, and you set the dv sub y over dt equal to 3. But as a vector, of course, that just means it's in front of the I hat and in front of the j hat. And then you integrate 4 with respect to time to get 4t. And that'll be the velocity as a function of time. Then you integrate, of course, that'll be the x component. Then you do the dv dt equals 3, and that'll give you 3t. And that'll be the y component of velocity as a function of time. Once you do that, then you have the velocity as a function of time, and to get the position as a function of time, you realize the velocity, which is v of t, is also dr dt. So you set dx dt equal to 4t, and integrate that with respect to time, so you end up getting 1/2 4t squared. And then you say dy dt is equal to 3t, and you integrate that to get 1/2 3t squared. Of course, it didn't say what the velocity was at any time, so you've actually, when you do that first part, getting the velocity by integration, then you have to use your initial conditions for velocity and stuff like that to get it. So let me show you on a piece of paper. So can I steal the screen for a second? So I'm going to go to my document cam. We've got A of t, which is dv dt, is equal to 4.0 meters per second I hat plus 3.0 meters per second j hat. We've got r of 0 is equal to 0 I hat plus 0 j hat. Okay, that's when they told us x is equal to 0 at t equals 0 and y is equal to 0 at t equals 0.
Mm-hmm.
So what I do now is I say, okay, well, v, if I integrate dv dt with respect to t, then that's just going to give me v of t. But on this side, it's going to become integral 4.0 meters per second dt times I hat plus integral 3.0 meters per second dt times j hat. Okay, the problem is you have to integrate from t equals 0 to some new time t. Okay, they didn't tell us anything about the initial velocity in the problem. At least I didn't see it.
Yeah, there were it was like a multiple question, so I think that was one of the things I figured out. Let me look and see what that was.
Okay.
Let's see. Okay, so v of t was 5t. Or, yeah.
Was 5t.
Yeah, vt was 5 of t is how it was written.
Okay, and that was it. Was there I hat or j hat with it?
Oh no, that was the whole velocity. The vx of or we already have those, but no, it said it just wanted 5t.
Oh, okay, so that's the okay. I get you 5t because that's the magnitude. Notice this is a 3, 4, 5 triangle. Y'all see the 3 and the 4.
Yeah.
So if you took the when I integrate this, I'll get 4t plus 3t, 4t in the I hat direction and 3t in the j hat direction.
Mm-hmm.
When you take the magnitude of that, that'll become square root of 3t squared, all that in parentheses, plus parentheses 4t squared, and that'll work out to be 5t. So they're telling us that the initial velocity was actually 0. So that helps. Cool.
Yeah.
Thank you very much.
Yep.
So I'm going to integrate that, and I'll say that, of course, the integral of 4 dt is just 4t. So I'm going to say 4.0 meters per second t in the I hat direction, plus 3.0 meters per second t in the j hat direction. So that's my velocity as a function of time, and the magnitude of velocity was equal to square root 4t squared plus 3t squared, which equals 5t. So I think you can see that this is right. In other words, what I would have had to do is this would have had 4t plus v0x, and this would have had 3t plus v0y. This just told me that v0x and v0y are 0, because
Okay.
when t is 0, this whole thing is 0.
Yeah.
So I now got v of t. That's helpful. And now v of t is actually equal to dr over dt, which you can all call r of t, of course. So the integral of dr of t, dt with respect to dt, is just r of t, and that has to be equal to the integral of 4.0. I'm going to leave off the units this time. T dt I hat plus the integral 3.0 t dt j hat. And that goes from t equals 0 to t, and t equals 0 to t. And remember, x of t, x of 0 and y of 0 was 0. So you don't have to have an x0 term and a y0 term either. So I think you can see that's going to be 1/2 of 4.0 t squared I hat plus 1/2 of 3.0 t squared j hat. And of course, you still need your units. Units in there have to be meters per second. And of course, you can multiply this 4 or by 1/2 to get 2, and you can get 1.5 for this one if you'd like. Does that make sense?
Yeah, that does. Thanks.
That's like the simplest way they can force you to do calculus in calculus-based physics class.
Yeah.
Is well, actually, the simplest is doing the derivative. The second simplest is doing the integral. So that's something they'll ask you over and over again. I would not be surprised to see that in many problems.
Okay.
Okay. Anybody else have any questions?
There was one more, just the last one. I don't know how. I just don't know what it was that they wanted me to do after I tried a few things.
You can share the screen again if you'd like.
Okay, hold on. Let me pull it up. Alrighty. Okay.
Man, I'm bald.
Okay, can you see it?
Yes.
Okay.
Okay. Calculate the horizontal distance traveled by the shot if it leaves the athlete's hand at a height of 1.80 meters. Okay. So this is that's a different problem. It's 3.35. A shot putter throws a shot with an initial speed of 15.0 meters per second and an angle of 36 degrees to the horizontal. Okay. Okay, so what's going to happen here basically is you've got a y component of velocity fighting gravitational acceleration. The y component of velocity, notice that's 36 degrees, so that's our special 3-4-5 triangle.
Mm-hmm.
And the hypotenuse is 15, which is 3 times 5. So that tells me the vertical component, which is the smaller of the two, will be 3 times 3. So that's 9 meters per second vertical. And the horizontal component would be 4 times 3, which would be 12 meters per second horizontal. Okay. But you can get that from doing 15 times the cosine of 36. That should give you roughly 12 meters per second horizontal, and sine 15 times the sine of 36 should give you 9 meters per second. So what you have is a vertical velocity of 9 meters per second going against gravitational acceleration. So what you need to do is figure out how long it takes for that to go from a height of 1.80 meters to a height of 0 meters. That's how long it'll be in the air. And once you have how long it'll be in the air, you just multiply that by the velocity in the horizontal direction, which is at 12 meters per second, times that number of seconds, and that'll tell you how far it travels horizontally, because the two motions are completely disentangled. So let me show you what I mean by that. I will steal the screen back and put it on my document cam.
So you said we knew it was the 3-4-5 because it was a 36-degree angle. So it doesn't have to be like exactly 30 for you to assume that?
Yeah, 36.1 is really it. So if they want 3 sig figs, they should say 36.1. If they want 2 sig figs, 36 should be fine.
Okay.
So this is 5 times 3. So this one is this the smaller angle? The other one's 53.9 or something like that.
Yeah.
So that one has to be opposite the big side. So this will be 4 times 3, and this would be 3 times 3. I'll say all have to be multiplied by the same number. So this one gives me 9 meters per second upward. And this one gives me 12 meters per second upward. So what I need to do is find out x0 is equal to 1.80. I think they gave us 3 sig figs meters. And what we want to do is find when x is equal to 0. Well, our equation for that is x is equal to 1/2 at squared plus v0t plus x0. So we know that 0 would equal 1/2 times negative 9.80. I'm calling up the positive direction. I'll leave off the units for right now. Plus 9.0 t plus 1.80. Okay. So I think you can see that's a quadratic equation. In fact, the quadratic equation is negative 4.9 t squared plus 9.0 t plus 1.80 is equal to 0. So you just use a quadratic formula. Negative b plus or minus square root of b squared minus 4ac over 2a. That'll get you the time. And then you're going to use basically the definition of average velocity. So average velocity is x minus x0 over t. But now I'm actually talking about x instead of y. So if I want to know the final position x, it's going to be x0 plus v bar t. But remember, horizontal velocity has no, since we're dealing with negligible air resistance, it has no friction, so the velocity is a constant. So we're just going to say it's equal to 0 plus 12 meters per second times whatever time we find from that. And that'll be how far away it landed. That's the trick with all projectile motion problems, is you've got a vertical motion going on that has gravitational acceleration, and the gravitational acceleration always acts like 9.8, whether you throw it up, whether you throw it down, whether you just drop it or whatever. It's always going to increase its speed downward by 9.80, or if it happens to be going faster than 9.80 on the way up, then it's going to decrease it by 9.8 until it gets to 0, and then it's going to start increasing it by 9.8 going downward. Once you work out the time constraints of how long the vertical motion gives you, then you just multiply that by the horizontal motion velocity, and that gives you the actual distance it travels, or the range, if you will.
Okay, so the 180 wasn't y, that was along the x vector. I thought that was for y, but I guess not, because it said that was like the height that it was.
Yeah, it was actually the height. It's just I use when I derive the equation x equals 1/2 at squared, I derive it in terms of x, but there's another one for y. So that equation that I first wrote and told you about, the quadratic formula, that was technically the y equation.
Oh, okay. Yeah, that makes sense.
So what they're saying is basically a shot putter threw it from about the height of his shoulder, and his shoulder's about 1.8 meters high.
Yeah. Okay. All right. Thank you.
They're not small people, those shot putters.
Yeah.
Okay. Well, let's go ahead and get started on some other problems. So what I have here is an inclined plane with a mass sitting on the incline and another mass hanging from it. The mass M1 is 10 kilograms, and the coefficient of static friction is 0.5. I've made the incline quite steep at 53.1 degrees, and what I want to know is what ranges of masses allow this thing to sit perfectly still. Okay, in other words, if you make the mass too high, it's going to be enough to overcome the force of gravity and the friction force and pull the block up the incline. If you make it too small, then the force of gravity is going to overcome the friction and the force of this and slide down the incline. So I want to find out what range of masses allow it to sit perfectly still. Okay, so in doing that, I am going to draw a modified coordinate system, like I always do. This will be my x direction, and this will be my y direction. Now, when I go to use coordinates like this, once I call this the positive x direction, anything that's consistent with this going in the positive x direction is going to have to be considered a positive direction as well. So in other words, I'm going to draw two free body diagrams, one for this one and one for that one. So when this guy goes down, is that consistent with this guy going up or with this guy going down? When M2 goes down, is that consistent with M1 going up, or is that consistent with M1 going down?
Going up.
I think y'all both said the right thing. Going up, yeah. So I have to call this the positive direction for M2 because I called that the positive direction for M1. Okay, there's ways to get around that, but I just found it's always easier to do this. So let me draw my free body diagrams. My free body diagram for M2 or M1 is this. I have a tension T at 53.1 degrees. That's actually along the x direction, so I could actually call that a blue vector, meaning it's in the positive direction. Then I have a gravitational force acting downward. That one should be a black vector because it's not along any coordinate systems. That one is M1 times G, which is actually equal to 98.0. By the way, Monday, I think I multiplied 9.8 times 10 and got 980. So you'll find that as a mistake in my notes, but I corrected it in the notes, or I just warned you that I had screwed up in the notes. So I apologize for that. I don't know what I was doing, but as soon as I hung up with you guys, I knew it was wrong. All right, and we also have, in the first case, I want to consider the block going up the incline. So this problem is going to be up the incline. The reason why I have to do that is because if the block's going up the incline, then friction is going to fight it by pulling this way. If the block's going down the incline, then friction is going to support it by pulling that way. So it's kind of a pain, but you got to do it, right? So what I'm also going to say is there's a friction force this way, F, okay? And that's equal to mu sub S times the normal force, which brings us to yet another point that the normal force is actually this guy. Okay, notice that's also a blue vector because it's parallel to the y-axis. So this force over here is just a tension T, that's an unknown. The normal force is also an unknown, but we can figure it out. What I'm going to do now is break this vector right here, this weight, up into components parallel to the X and Y axes. So in the Y direction, it's clearly a negative vector. So I made it red. And then, of course, in the X direction, it's also a negative direction. So I made it red. So this one's going to be M1G times, now, as I showed you before, when I draw this vector right here, which is this vector, that makes this angle, which would be this one right here, 90 minus 53.1. And since this whole angle is 90, this one must be the other 36.7 or whatever, 36.9, I think it was. Yeah, 36.9 is what it's supposed to be. Yeah, so that other problem, by the way, you might want to go ahead and use trig functions. Don't use that 9.0 because that they only gave you 36, and 36 is not quite close enough to 36.9. So keep that in mind when you're doing that problem that you asked me about a second ago. But the main thing is this angle right here is going to be, indeed, this one would be 36.9 and this one would be 53.1. So we got that. So this one's going to be the opposite side. So this will be M1G sine 53.1, which I'll compute that in a second. And this one's going to be M1G times the cosine, because it's actually adjacent. It's touching the angle of 53.1 degrees. So I might as well calculate those just for the heck of it. 9.8 times 10. And I'm doing this just to be a pedantic because I keep making up careless mistakes. I know for a fact that cosine of 53.1, if you actually look at the 3, 4, 5 triangle, you can tell that cosine of 53.1 is 3/5. So, but still, I'm not taking any chances. I'm going to multiply that by cosine 53.1. And I get 58.8. Yeah. And I'll carry one extra digit, so it's 58.84 newtons. Oh, I wrote that on the wrong one. And I'll underline this. I will put a bar through that to remind you that, oops, that's Mr. Younger being a crackhead. Now I'm going to do trig sine 53.1. And this one gives me 78.37. Again, I'm keeping an extra digit just to make sure everything is kosher. So in other words, I do multiple calculations using these numbers. I don't want to round repeatedly or I'll get an undue amount of error. Now I can take Newton's second law in the y direction. So the summation forces in the y direction equals mass times acceleration in the y direction. This is a case where I don't want the block bouncing up and down on the block on the incline. So the acceleration in the y direction has got to equal 0. That tells me all the forces must add to give you 0. That means Fn minus 58.84 newtons is 0. That means the normal force is in fact 58.84, extra digit again, newtons. So that's what I get from the summation of forces in the y direction. The summation forces in the x direction equals mass times acceleration in the x direction. In this case, remember, I'm trying to find a mass where this thing is just about to break loose. In other words, I want this friction force, which can be, as small as it needs to be, but it can only go up to a maximum amount, and that's why I put equal to mu s times the normal force. So if I make sure that these two are just enough to, these two plus this one are just enough to cancel one another out, then I figured out the maximum mass for M2, okay? So I'm going to take this as the acceleration again equals 0. This will give me t, that's in the positive direction, minus 78.37, carrying that extra digit, minus the friction force, which is 0.5. I'm going to go ahead and act like I gave you 3 sig figs on there just to keep everything nice. And remember, static coefficient of friction, as is the kinetic coefficient of friction, has no units. And I'm going to multiply that by the normal force, which we figured out was 58.84 newtons, again, carrying that extra digit. All that has to equal 0, and that actually allows me to determine my tension. So trusting that all this is right, I'm going to do 78.37 plus 0.5 times 58.84. And that should give me my tension, which appears to be 107.8. Again, carrying an extra digit there, okay? Now I've got to do the free body diagram for the other mass. The free body diagram for the other mass just has a mass M2, and it has acting on it a force which is in the positive direction, downward in other words. That force would be M2G, like so. And the force acting upwards is actually a negative force, and that's the tension in the rope. Notice I use the exact same tension. So the deal with a pulley is an ideal pulley should have exactly the same amount of tension on both sides. So according to this mass, this thing thinks, oh crap, there's some magical rope that pulls this way. And then of course this guy that wants to fall at 9.8 meters per second is thinking, wow, there's some magical rope that slows me down and therefore is pulling me that way. If the pulley is ideal, that means it's massless and frictionless. These two tensions should be exactly the same. That's why I don't subscript them. When we start dealing with rotational mass and friction, I can actually change it to a T left and a T right and then find out exactly what the tension differences are. But right now we got that. So now the summation of forces equals mass times acceleration for this one. I want this tension to be exactly what's necessary for that other part. And in fact, that's just enough to stop this from going downward. In other words, I want the acceleration to be 0. So that gives me M2G minus T is equal to 0. So that means M2G is equal to T, which means M2 has to be, in this case, if it's any bigger than this, it's going to actually cause it to accelerate. So I'm going to say M2 has to be less than or equal to 107.8 newtons divided by 9.80 meters per second per second. So M2 has to be less than or equal to 10.998, so I might as well call that 11.0 kilograms. Okay. So that's one of the answers. That's the biggest mass it can be. If the mass is any bigger than that, hanging over here, it's going to cause it to go up the incline. Now I'll do the same thing for down the incline. I think you can see down the incline, the only thing that's going to change is this tension is going to be pulling this way and the friction forces are going to be pulling this way. So we still get the same normal force and all that good stuff. The only thing that's going to change is, in fact, this equation, and this equation is going to have a plus here. So I'll say the summation of the forces in the x direction equals mass times acceleration in the x direction. But again, I'm considering that special case where the tension and friction is just enough to counteract this, in which case the acceleration will be 0. So I end up getting T minus 78.37 newtons plus 0.5 times 58.84 is equal to 29.42. And that's all equal to 0. I know that got really small there. I'll rewrite it right here. T minus 78.37 newtons plus 29.42 newtons is equal to 0. That means the T has to be, in this case, 29.42 or 78.37 minus 29.42. And that gives me 48.95.
Where did the 29.4 come from?
I basically took this part right here and multiplied them and got 29.42.
Oh, okay.
Okay, so notice the only difference between that equation and this equation is I changed the direction of the friction. So that one became a plus instead of a minus. That's why that plus is there. Okay. So now I've got the tension, and of course the other equation still applies. It's still M2 minus G equals 0. So T has got to be, M2 has got to be T over G. So in this case, I'm going to say, all right, well, M2 has to actually be, in this case, greater than or equal to that amount. So I'm going to say M2 is greater than or equal to T over G. So this G, or this T, is 48.95 over 9.80 meters per second per second. And I get 4.995 basically, or 4.995, yeah. Which means M2 has to be greater than or equal to essentially 5.00 kilograms. So the range that we found was 5 to 11 kilograms, which is kind of neat because I just made those numbers up and got really nice whole numbers. So a 10 kilogram mass at 53.1 degrees requires something between a 5 and an 11 kilogram mass if the coefficient of friction is 0.5. So see how we had to break that problem up into two separate problems? One where the mass was actually, M2 was actually big enough to pull it up the incline so friction would fight it by going backwards, and the other one where the mass was so small that it just barely held it from sliding down the incline, in which case the friction would be in the positive direction. And by doing that, we were able to get a nice little range of masses. Any questions on that?
I got a question. So the 5 kilograms is to keep it in place, and the 10 kilograms is to make the box number 1 go up the climb.
The 11 is, yes. You said 10, but yes, the 11 is. So if you used 11, or if you used 11.1 kilograms hanging, then the box would slide up the incline. If you use 4.99 kilograms, the box would slide down the incline.
Oh, okay. That makes sense. So within the range, the box is going to stay put.
Exactly. It's a neat problem, isn't it? Now, if you go into engineering, you'll take statics and dynamics, and they'll teach you very fundamental logical rules that you apply to all these instead of having to think it through at each point. And that's kind of nice. That's rewarding because, you know, in the physics world, we sort of make you do the creative part of figuring out, well, what's going to happen when it does this? Well, they give you very set rules in a dynamics class and a statics class on how to deal with all the possibilities. So I'll just tell you, it gets a little easier when you take statics and dynamics and engineering than it is right now in physics, at least in that part. But you're going to be diving so deep on all the other stuff, you'll be thankful for having these little life ropes that they give you. So if any of y'all are going for engineering, that'll hopefully give you a little bit of reassurance.
So the main difference when we were finding the range for M2 is, was it that positive sign or that negative sign in the first one and the positive sign in the second one, or?
Exactly, because what happened was, if you're thinking about this block being so heavy that it's pulling the incline, pulling the block up the incline, then the friction is going to help hold the block in place by pulling this way, which is the negative x direction, hence the negative sign.
Oh, okay. Okay, that makes sense.
And then when you're thinking about the block being so light that the other block is going to slide down the incline, then the friction's helping again, in that case, by pulling up the incline, which is the positive direction.
Yeah. Okay.
Make sense?
Yeah.
Yeah, it's kind of neat. That's the one good thing, and this is why I like physics, is it's until you get to quantum mechanics, it's completely reasonable. It's completely logical. Everything makes perfect sense that it's exactly that way. It gets a little abstract when we get into electricity and magnetism, but at least even then, if you can figure out how things work, it works fairly straightforwardly. So what I'm going to do now is, I already gave you an idea about how to calculate the acceleration of the moon. What I'm going to do now is give you a simple example of calculating basically what we call Kepler's third law. And there's a much more robust way that you can do it. You can find it in your probably in your Calc 2 portion of your calculus textbook. But what I'm going to do is pretend like there's a mass that is the sun. I'm going to call that big M. And then I'm going to pretend out here there's a mass little m that's a planet. And I'm going to assume that it's going in a circular orbit whose radius is r. Okay, actually, let's make it a big R. Okay. What I want to do is work out the physics of this so you can make sense, and then I'll actually end up deriving Kepler's third law, which says the square of the period is proportional to the cube of the semi-major axis of every orbit. So what we're going to do is we're going to assume this this individual planet has a velocity v, which is of course going to be equal to 2 pi times r, that's the distance traveled, divided by the period t. So that's the period we're going to use. And r would be our radius, in reality, in ellipses, that's going to be the semi-major axis. So you'll sometimes see that written as a in astronomy textbooks. What we have here is the summation of forces is equal to mass times acceleration. Well, right here, we have a force acting on it. That's the gravitational force. According to Newton's second law, the gravitational force is G m over r squared. That's what Newton was able to discover. He found that the force of gravity is directly proportional to the product of the masses. So if I replace Earth with something twice as heavy as Earth, then the force of attraction between Earth and the sun would be twice as big. Similarly, if I replace the sun with a sun that's 3 times as massive, the force would be 3 times as big. If I did both, the force would be 2 times 3 or 6 times as big. Not only that, if I made the planet twice as close, instead of being 1 astronomical unit away, I made it a half an astronomical unit away, the force of gravity would in fact be 4 times larger, because 2 squared is 4. 1/2 squared, of course, is 1/4. Dividing by 1/4 is multiplying by 4. So that's the actual force acting on it, and that's the only force acting on it. So the whole left-hand side of F equals ma is just G m over r squared. So I get G, the gravitational constant, times the mass of the planet times the mass of the sun over r squared has got to equal the mass of the planet, because that's the one doing the accelerating. We're pretending this mass is so huge that it doesn't even wobble. Okay. In reality, when we work it out, it does wobble, and we can take that into consideration. It's just more complicated. Okay. But what we learned last time by doing that, calculating the acceleration for an object going in a circle, we found that the acceleration to maintain a circle is v squared over r. So I'm going to say v squared over r like so. So that's the entirety of Newton's second law. But I can make it a little better. For starters, I know that the m's cancel out. So it turns out this velocity is independent, really, of the mass of the individual planet. So that's kind of neat. That means any object you put there, whether it be a little satellite or a planet Earth or a planet Jupiter, which are obviously three very different extremes, you're still going to get the exact same orbit. So if we replaced our planet with Venus or with Jupiter, it would still orbit at the same rate. Now, what I can do also is replace this v with 2 pi r over t, and I can also cancel out one of these r's to leave an r in the bottom here. So now I've got g m over r, which, by the way, if you calculate that, is 9.8 meters per second, because this little g is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. So that's the actual constant. If you look up the mass of the Earth and the radius of the Earth, you'll find that this computes to be 9.8. Now the v squared is going to be 4 pi squared r squared over t squared. And t is the time required for the planet to go from here to here. And of course, on Earth, that's about 364.25 days, roughly. So we can now get the relationship that we're really looking for. I'm going to manipulate a little bit by saying g m over 4 pi squared is equal to, and what I have here is when I pull that r up top, that's going to become r cubed, and t squared in the bottom. So remember what I told you, the square of the period is proportional to the cube of the semi-major axis. So I could actually write this as t squared is equal to 4 pi squared over g times m times r cubed. This is a constant, right? This is the gravitational constant of the universe. This is the mass of the sun. Pi is a constant, 4 is a constant. So we see this is truly a constant. And in fact, the square of the period is proportional to the cube of the semi-major axis. In fact, what Kepler did was he had worked out what the periods and the rate and the distances had to be, all in terms of the Earth's one. And he made a plot of t versus r, and he got a curve. Then he made a plot of t versus r squared, and he got another curve. So he knew that wasn't right. So he did t versus r cubed and got another curve. T versus r to the 4th got another cube. Another curve. He kept doing that until he finally got the combination of t squared graph versus r cubed graph, and he got a straight line. And at that instant, he knew that t squared is proportional to r cubed, and that turned out to be a fundamental law of nature. In other words, when we find other objects orbiting other objects, they have the same relationship. The square of the period is proportional to the cube of the semi-major axis. So that's a really, really big deal. So that's Kepler's third law, and that's a nice little exercise. Again, you can calculate that all day long if you want to do different planets. I recommend you do that, but I got about 5 minutes left, and I need to do one more problem, and that's a car banking around a curve.
Go back for just a second.
Yes, go ahead.
I just need to see that paper 1 sec.
Oh, yes, no problem, sorry. So with the car banking around the curve, we're going to use the same sort of scenario, but what we're going to try to do is we're going to try to design the curve so that the car doesn't need any friction whatsoever between the tires and the road to keep from sliding off the actual ramp, okay, off the curve, the berm, if you will, if you're a NASCAR
I'm done
person.
with it.
Okay, thank you, appreciate that. So what we have here is an inclined plane like this, of some angle theta. So there's our car, right? The forces acting on it, of course, are going to be, and this one I'm actually going to keep my vertical coordinate system. So I'm going to say, in fact, that x, I'm going to point to the left, and y I'm going to point up like so. Okay. So my forces are the weight, which is the car's mass times gravitational acceleration. And then I have a normal force, which actually is at this angle. And actually that one should be black because it's not along any coordinate direction yet. Okay. So that's the normal force. And if you can tell, this angle is theta right here. This angle would be 90 minus theta. And if you attach this here, you'd see that this would be right along there. Trying to work that out. It turns out that that one should be, yeah, that should be theta as well. Okay. So the y component of F normal would be that one, and the x component of F normal would be that one. And of course, this is Fn sine theta, and this guy is Fn cosine theta. I think you can see that the summation of forces in the y direction equals mass times acceleration in the y direction. We're again dealing with a static case. I don't want the car bouncing up and down. The acceleration is going to be 0. So I end up getting Fn cosine theta minus mg is equal to 0. So that tells me that, in fact, Fn is equal to mg over cosine theta. So we've now worked out what the normal force would be. Now, the summation of forces in the x direction equals mass times acceleration in the x direction. This is not a case where the acceleration is 0. In order for this car to actually make the turn, it has to have an acceleration v squared over r. So in this case, the only force that's providing that is the component of the normal force that is perpendicular, basically, is parallel to the plane of the actual rotation. Okay, so it's that guy right there. So I'm going to say Fn times the sine of theta is going to be going to have to be equal to mv squared over the radius of the turn. So a typical value might be v is equal to 60 miles per hour, and r might be 100 meters, and I'll have to convert that to meters per second, of course. But now you can see if I plug in mg cosine theta for Fn into equation 2, so 1 into 2, I get mg over cosine theta times the sine of theta is equal to mv squared over r, which is nice because, one, the m's cancel out, which means I don't have to do a different design depending on whether it's a Mack truck or a Honda Prius, or excuse me, a Toyota Prius or something. And also I get sine over cosine, so that's kind of nice. It tells me that tangent theta has got to equal v squared over r. So that's our actual result. Tangent theta equals v squared over r. So let's try that real quick. I know we're about out of time. I'm going to do my 60 miles per hour at 100 meters and see what the bank is. So 60 miles per hour, I'm going to do times 5,280. That gives me feet per hour, times 12. That gives me inches per hour. And then times 2.54. That gives me centimeters per hour. And now I divide it by 100, and that gives me meters per hour. And now I multiply that by 3,600, or excuse me, divide that by 3,600. And that gives me 28 or 26.8 meters per second. So theta would equal the tangent inverse of 26.8 meters per second squared over 100 meters. So I'm going to do square that, divide it by 100, and now I'm going to take the inverse tangent of it. And I get, wow, that's a really big angle.
What happened with G?
Oh, thank you. That's exactly why. It's G times R. Thanks. Nice. That's why my angle was getting ready to be some crap. Yeah, so I lost G. It's right here. So it ends up being GR. I should have known that. The units didn't even work. So that'd be 9.8 down there times 100. Thanks. Nice catch, dude. So let me see. 26.8224. I'm going to square that. I'm going to divide it by parenthesis 9.8. Thanks for catching that, man. That would have gave me it was already giving me really bad results. And now I'll take the inverse tangent of all that. I get 36.2 degrees or 0.3 degrees. So that's not too bad of an angle. That's, 3, 4, 5 triangles, what we're looking at there, basically. But yeah, if you want to go 60 miles per hour around a curve that's only 100 meters in radius, you're going to have to bank the turn at about 36.3 degrees above the horizon. So that's a very typical, very neat little problem. I hope that lets you see how you can use mv squared over r. You'll see there's some more examples in your book of using mv squared over r. For instance, if you ever held a string with a mass on it and you started spinning it around your head, over your head, the tension in there had to provide that mv squared over r force. If it didn't, if it was incapable of doing so, like you were say using 10-pound test string and mv squared over r turned out to be about 20 pounds, then you'd end up busting it. That also happened to a poor group of people that decided they were going to do a big swing off of the Golden Gate Bridge. Guy, didn't have a real physics course, never had a physics course in his life, evidently. Got a group of people, like 8 people together. They were all going to tie themselves together, connect a big cable to it, and jump off the Golden Gate Bridge and swing. And he basically added up all their weights and found they weighed like 2,000 pounds, or actually it was like 1,200 or something. And he found some cable that held up to 3,600 pounds. He's like, well, that's more than enough weight. Well, it is, but the problem is, in order to keep it in a circle, you got to have their weight plus mv squared over r, and that actually exceeded the cable. The cable broke. I think one person's paralyzed, quadriplegic for life now. He got sued. Really, really bad scenario. So this is a case where knowing some physics can help you. Remember, it's not just mg, it's also mv squared over r that you need to supply if you want to make a swing. All right, anybody have any questions? All right, well, let's meet back at 12:20 for lab. Does that give everybody enough time? That's like 25 minutes from now. Those of you who have lab, of course.
Yeah, I think that's enough time.
Sounds good. All right, folks, I'll let you go, and feel free to ask me questions during lab and all that good stuff. I've already posted the lab stuff, so you can go check that out if you'd like. And I'll see you in about 25 minutes.
Thank you.
You're welcome. Thanks again for catching me on the G. Yes, ma'am.
So I just wanted to ask you about, so like with the homework and the reading the text, and obviously it's like been taking me a really long time.
Right.
And so I was just wondering if like maybe it seems like it's a lot, if like we could be given a little bit more time for the homework, or like have it a little bit more condensed. Maybe
Yeah, yeah, I'll see if I can do that. The thing is, I try to make sure you guys have an assignment a week, so y'all know every Sunday you're going to have homework due.
Yeah.
So I will try to see if I can either break them up a little bit easier, so that you'll have maybe half one Sunday and half the next Sunday or something like that. And also the other thing is I need to make sure the homeworks are due for a given chapter before that chapter is tested. that's the other part that I'm trying to work against. But I'll see if I can't give y'all more days on homework.
Okay, thanks.
And also, it's always good to read your text. So you're wanting to try to get where you can read that first reading fast.
Yes, definitely.
And that second reading is going to take a little longer.
Mhm.
So, but if you find that you're still not getting it after the second reading, I would say you're probably you're at a point of diminishing returns if you're trying a third reading. So don't try that so much. Start asking me questions at that point.
Okay. Yeah.
Okay.
Yeah, I haven't I did that for the last chapter and I got some help. I don't know, but it's like I understand it when I read it, but it was just the specific homework problems. There were factors that I just forgot about. So, but yeah, I'll definitely let you know if I still don't understand it after reading it over those 2 times.
Right. It's weird when you're reading a physics book because sometimes you'll have 4 paragraphs all explaining why we know what we know.
Yeah.
And then you'll have one sentence that's really the critical part of the whole friggin' chapter.
Yeah.
So you got to read with a fine-tooth comb, but then you also got to sort through the stuff because a lot of it's just telling you why we know what we know, which is important to know. So we're not doing dogma, but at the same time, the relevant fact of how to solve problems came out in that one sentence. So just keep it up. But I'll work on seeing if I can figure out a way to give y'all more time on your homeworks.
Thank you. And then there's one thing. So, of course, I hate to say this, but especially since I kind of had to take more time on the past chapter, I have to go out of town this weekend. And I was wondering if the chapter 5 homework, if that could be extended to like Wednesday.
Oh, yeah, I was planning on extending that one anyway. So I'll actually extend that to next Sunday.
Just making sure I had that base covered. I wasn't sure.
Will you be able to get your test done by Monday?
What's that?
Will you be able to get your test done by Monday?
Yes, I will be able to do that.
Okay. Yeah, what I'll do is I'll make that test due Monday at 10 a.m.
Okay.
That'll give you just a little bit more time in case you want anything. But like I said, I'm gonna give you multiple attempts again. So
Okay, thank you.
thanks for letting me know, Emma.
Yes, thanks for your help.
You're welcome. Bye, everybody. Unless you have other questions.
I have a question about the labs and stuff. I know you gave us a chance to redo them, and I know that's due on Friday, right?
Yeah, that's when I was planning on grading them. So whatever you get done Friday would be helpful to me.
That
would be fine.
Can we redo all, because because the same mistake I made on the first lab I made on the second and third, so I was working on those 2. So can I?
Gotcha. Why don't you turn in number 2 by Friday, or number 3 or number 4, but preferably number 2, and then get the other one as quickly as you can.
I was working on them 2 days ago, but I think I need to redo because I scanned them in, but you can still see the pencil, so I'm just gonna get the Word document and retype them to make it look a bit nicer.
I don't mind at all the pencil marks being in there. It's not about that. It's more about, can I tell the difference between handwritten, between what you've entered and what the manual has in it. So if it's handwritten, pencil or not, I can tell what's there. Unless you've got a lot of scribbles on it, then that might be a bit of a problem.
Because I got I think my problem was that I just didn't use like red or blue pink, or no, red or blue ink. So I was just rewriting everything in red.
Yeah, try to get lab 2 done by Friday, and I'm I normally don't grade more than 1 lab a week. So if you got 2 done, I wouldn't even notice you were behind.
Okay. I'm just editing them because I think they have the same problem as like lab 1 with not having the data in a different color or that stuff. So I just want to make sure.
When I say have 2 done, I mean lab 2, not 2 different labs. Just
okay.
Get lab number 2 done by Friday. That would be more than sufficient for me.
Okay. Okay. Thank you.
No problem.
See you in.
Tell your friends.
I'll see you in 20 minutes.
I'll be there. How about you, Maria, or Mimi, or Jacob? All right. Well, I'll see you, folks.